Hi everyone, this is Anil Bhatia again from PAT Fun Begins, Practical Architectural Training, a unit of ADS, Architects Design Studio. In our last few videos, we had covered up topics such as air conditioning and waterproofing. In the last one, we had started understanding structures. We had discussed how to read the reinforcement drawings for a raft with a practical example of a site. We had understood what bottom reinforcement was, what top reinforcement was, and also this was totally explained in three drawings, and these three drawings could make us understand raft reinforcement for sites. We had to next study how to tie reinforcement for columns and for beams for rafts, and also how to read reinforcement drawings for RCC retaining walls. So let's start with reading reinforcement drawings for columns first. The first thing in the drawing on the left is to look at the column schedule. This shows the size of the columns, which in this case is 450 mm into 70 mm. The next thing this schedule shows is the mix of concrete required. Again, have a closer look at M30. So M30 is the mix of concrete required. The next thing is the number of bars and the dia of the bars. In this case, we have 8 numbers of 25 dia bars. Next, we can see the stirrups required. This schedule shows at the bottom that we require 8 tor stirrups, that means 8 dia stirrups at 100 center to center, and also 8 tor at 200 center to center. So what are these two areas A and B which are shown in the stirrup schedule? Let's look at the column on the left. Now this is the elevation of the column. There are three zones. First is the LO zone at the upper level. The second is the LO zone at the lower level. Have a closer look. Then there is the central zone where overlap of reinforcement. That means reinforcement here can be joined. So this is the area where overlap can take place. This area in between is called the splice zone. In all these areas, both LO zones and the zone in which overlap takes place, the stirrups are closer to each other. Have a closer look. The stirrups are closer to each other here. So 8 tor at 100 center to center is meant for these areas. And in all other areas shown as B, just look at the B we have marked there. We can have stirrups 8 tor at 200 center to center. The next information shown is the number of stirrups. There are two number of stirrups of different shape. One is a rectangular shape. Look at the schedule on the left. One is a rectangular shape and the other one is a trapezoidal stirrup. Now both these stirrups are called one set of two stirrups. It is called one set of two stirrups and they are kept joined to each other. And we say this set of stirrups shall be 8 tor at 100 center to center or 200 as mentioned above. So this clearly is shown in the diagram on the left. Now have a closer look. There is a set of stirrup at every point. So that means there are two stirrups at every position. There is one more information in this schedule. This schedule shows that this information is for C1 column. That is the name of the column, which is always written at the top, and on the left hand there is another information, that this information in this schedule is from foundation level to ground floor level, and above that it may change. Now, how do we decide till what height the column steel is to be erected? For this, we must understand which is the area where we are allowed to have overlaps, joints of bars in a column reinforcement. Now, let's take a look at the column reinforcement again. Have a look at the diagram on the left. There are two zones in the height of the column where we are not allowed to have laps in the reinforcement. The base height mentioned as LO, which I had mentioned earlier also, and the top height mentioned as LO. In between these two areas, we are allowed to have laps in reinforcement. The areas where we can't have laps are called no splice zones, and the areas where we can have laps are called splice zones. Now, how do we calculate the no splice zone height? Look at the new diagram on the left. LO depends on three criteria. The first one is LO shall not be less than the larger lateral dimension of the column. So if the column size is, let's say, 600 by 900 mm, then LO cannot be less than 900 mm. The second criteria is that LO cannot be less than 1/6 of the clear span of the column, which is shown in the figure. Clear span means under the beam and above the raft. This is for the basement. So if we assume a floor to floor height of, let's say, 4.5 meters, which is shown in the diagram, and a beam size above of 600 mm, then clear span is 4500 minus 600, which is equal to 3900 mm or 3.9 meters. So LO cannot be less than 3.9 divided by 6, that is 1/6, which is equal to 650 mm. The third criteria is that LO can never be less than 450 mm. So out of these criteria, if we calculate and if we check in the example here on the left, we can finally deduct that LO is 900 mm minimum. We have now got the size of the no splice zone, 900 from beam bottom and 900 from raft top. So we hence are left with 3.9 meters, which is the total height, minus 1.8 meter, that is 2.1 meters, which is shown in the figure. This is the area where we can have laps in the reinforcement. Thus, our splice zone is 2.1 meter in this case. The next splice zone will similarly come on the next floor, again with similar calculations for that floor. So we now know that laps in reinforcement can either happen within this 2.1 meter of splice zone in the basement, or they can happen in the upper floor splice zone and not anywhere else. Now, how can the laps be managed in this 2.1 meter, and what are the further rules for this? Here we have to understand one important fact. All bars cannot be lapped in one zone. Why is this so? Here it is very important to understand this. The steel in columns is so designed that the minimum sectional area of steel in a column should not be less than 0.8% of the sectional area of concrete. For example, in the column size here, which is 600 into 900 mm, the cross-sectional area of concrete is 900 into 600, that is 5,40,000 square mm. Hence, minimum steel required is 0.8% of this, which comes to, as per the calculation, 4320 square mm. Now, let's calculate the sectional area of a 25 dia bar with the formula pi r square. It comes to 491 square mm as is mentioned there. So, we shall require a minimum of 9 numbers of 25 dia bars, because 4320 divided by 491 will give you 8.79 bars. So we will need 9 bars. And what's the maximum sectional area of steel allowed at any given section in the column? That is 6%. So we can't have steel more than 6% of sectional area of concrete in any zone. In most column designs, the sectional area of steel comes to 4% of sectional area of concrete. So during overlap at one place, the sectional area shall become double, that is 8%, 4 from top and 4 from bottom. But 8% is not permissible. 6 is the maximum which is permissible. So how do we achieve a maximum of 6%? So we try to overlap half the bars in one area and half the bars in the area above within the splice zone. So you can have a look again at the drawing. In our case, the splice zone is 2.1 meter. So we can have two such areas of overlap. One is the area above, which is 1.05 meter, and one is the area below, which is 1.05 meter. So half of the reinforcement can be overlapped in the lower half and half can be overlapped in the upper half. Now, what is the length of lap required? This again depends on the strength of the concrete. We generally say 40 times the bar dia, but that's only an approximation, like a thumb rule. There is a chart for calculation of this overlap. Let's look at this chart and let's look at 25 dia bars for a concrete of M25 grade. We require an overlap of 971 mm. Have a closer look at the areas marked in red. 971 mm. And for a 32 dia bar, we require an overlap of 1243 mm in M25 grade concrete again. So that means for M25 concrete, in our case, we can't use 32 dia bars as the overlap is 1243, which is more than what we have, 1050. Hence, if we have to use 32 dia bars, we shall have to increase the strength of concrete to 40 grade, M40 grade, when the overlap required, in this case M40, it is 956 mm. Now we are clear as to how much overlap is required, and we are also clear how we can achieve this and how we can manage this within the splice zone. Now, what happens when we have a floor to floor height of, let's say, 3.6 meters? Let's check this out and let's assume that the column size has not changed. It is still 600 by 900 as shown. So LO will remain 900 as per our calculations, and total height below the beam is 3 meters. After deducting LO on both ends, which is 9.9.9, we are left with a height of 1.2 meter as the splice zone. So in this 1.2 meter, we have to create two overlaps. That means each overlap cannot be more than 0.6 meter or 600 mm. Now let's look at the chart again. It is easy to understand that if we have M40 grade concrete, even then we cannot use the bars more than 20 dia, because if we use 25 dia, then even with M40 grade we require an overlap of 719 mm, which is more than 600 mm. So if the column size is reduced from 600 into 900 to some lesser size, we can then reduce our LO and hence increase the area of the splice zone. In that case, we may be able to use 25 dia bars. Hence, when floor to floor height is less, the engineer has to design accordingly. That is the reason that the engineer requires all this data of heights of each floor before he can start his structural design work. Hence, we have understood why all bars in a column cannot be overlapped in one zone, and we have to stagger the overlaps. The next important thing is the stirrups. The distance of center to center of stirrups is reduced in both LO zones, which is the top zone and the bottom zone, and they are also reduced in the overlap zone. So we have hence understood where exactly overlap is possible in column reinforcement. Now we can decide till how much length reinforcement of columns can be erected. So let me put it this way, that we can choose to stagger the reinforcement so that we can maintain the overlap within the splice zone. So we can also decide the lengths of the reinforcement now to be cut and erected by keeping in mind the criteria of the splice zone. Let's look at the model of the column. This is the bottom reinforcement of the raft, part of it, and this is the column placed on it. Now these are the main bars of the column which are fixed to the bottom in this manner. They are fixed to the bottom reinforcement of the raft. Look at the bending of this reinforcement of column bars. As explained by me earlier, this is the lower, this is the lower LO, and the upper LO will come somewhere here. So this is the lower LO, which is the no splice zone. This is the way bars are staggered. So this bar is longer, then this bar is shorter. These 4 bars are longer and 4 bars are shorter. This is the way bars are staggered for overlap. So half the bars are overlapped in this zone and half in this upper zone. This total area from here to here, this is the splice zone, which is the stirrups are colored green in this splice zone. This total area is the splice zone. These are the stirrups in the lower LO area. You can see that they are tied close to each other at a distance of which is very, very less, and it is as per the structural engineer design. And now this is the upper length of the bar which is overlapped. Have a closer look now. So this is the upper overlap, and again they are staggered because this is going to meet this area and this is going to meet this area. So you have staggering of reinforcement here. Now we fix the upper lap of the column with the lower lap, and this green area, this shows the overlap area, and this is the splice zone, and this upper area is the upper yellow, and this lower area black one, these two black ones are the lower, this is the lower yellow. Now we have seen that in most of the areas the stirrups are closed. This yellow and this yellow is the only area where the stirrup is at a distance of 200 center to center. Rest in all areas the stirrup is at 100 center to center. Now we have actually understood where stirrups are 8 or at 100 center to center, these three zones 1, 2, 3, and in which part stirrups are at 200 center to center, which is only this and this. There is one more thing to understand in stirrups, and that is the special confining zone. Look at the base of the column. These red stirrups here are actually part of the raft, and they are supposed to be, these stirrups are supposed to be close together for at least 300 mm into the raft. So I'll show you the bottom raft portion also. So now we have the lower reinforcement of the raft, the upper reinforcement of the raft, and this red zone is 300 mm into the raft where we have the stirrups which are at 100 mm. This red zone is called the confining zone, special confining zone. In this zone too, the stirrups have to be at 100 center center. And that's it. We are through with this topic. This topic was slightly technical and maybe exhaustive and boring, but then some topics are like that, and we have to accept this in our field. We have to next understand about raft beams and also about RCC retaining walls in a basement. We shall understand these in our next video. After that, we shall move on to the RCC roof study. Hope this was informative and you shall be able to read these structural drawings with ease at the site. If you have any questions, then please note down our email ID given below. We shall be happy to answer any of your queries. Again, I must mention my team which has helped me present this. My staff, Pooja and Shubham, who have done the main presentation, and the present batch of interns who have worked really hard to prepare the model: Ayushi, Sanchi, Priyanshi, Manvi and Yukti. Till our next video, bye, take care.